Okay, we're going to look at another optimization problem. So we have several kinds of word problems that we're working on in this unit. So one important thing is to distinguish which kind of word problem it is. So the optimization problems will ask you to optimize or maybe maximize or minimize something, or it might say most or least, highest or lowest, any word that is synonymous with maximize or minimize. So this one is asking us to maximize something. So we want to be sure that we read through the problem carefully, right? So we've got some information about apple trees, how much each apple tree produces, some information about additional trees being planted and how that will affect the yield of the bushes of apples. And then here's what it's asking us to find. How many trees should she plant? And this is what we want to maximize or minimize. So first step is always read through the problem carefully, identify things that are known or unknown, and what it's asking you to actually do, maximize or minimize. All right, and then I need to write down an objective function that I'm able to maximize or minimize. So sometimes it's obvious if we have a box or something like that, we might have dimensions of a box to label and something about area of a box or perimeter of a box. A problem like this, I think it's a little bit harder to identify what exactly your variables are going to represent and how you're going to then write down this function that you want to maximize or minimize. Okay, so digging back into the information that's given, we're given some information here about number of apple trees and how many bushels of apples each tree will produce, and we want to maximize the harvest. So the harvest would be number of trees times bushels of apples per tree. And so that's what we want to maximize, but we're not going to necessarily leave our numbers at 20 apple trees producing 110 bushels of apples each. We want to know how many trees she's going to plant here to maximize her harvest. So there are a couple of different ways that I could start this problem. The simplest way to start problems like this is actually to use this information and let our variable represent this quantity, each additional item. So these are kind of typical problems that we come across in a business calculus class. And whenever I do any problems like this, this is usually what I let my variable represent, how many additional items. In this case, it's trees. There are other ways to do the problem, but I think this one, the equations turn out easiest if you let your variable represent how many additional trees. Okay, so once I've identified what my variable is going to represent, I now need to write down an objective function. That's the function that you want to maximize or minimize. All right, so here, what we want to maximize or minimize is our harvest function. So I'm going to call that H. And then thinking about how to write that down. All right, so I'm going to do a little scratch work over here of how you might think about what's going on. I actually already mentioned a little bit of this. At the beginning, they gave us some information about her estimates that if she plants 20 apple trees per acre, each tree will produce 110 bushels of apples. I should write bushels of apples, not just apples. So 20 trees, each tree produces 110 bushels of apples. And so 20 times 10 would be the harvest, number of trees times how much apples each tree produces, right? So, and then I know that based on estimates that for each additional tree, so 21 trees per acre, the tree's yield will decrease by 5 bushels of apples. So this will go down by 5, so it would be 105, and kind of so on. And so I'm just writing down some numbers here, looking at patterns, so that I can think about how to write this function that I want to write here. So the number of trees is changing based on number of additional trees per acre. the bushels of apples produced is also changing, and her harvest would be the product of those two things, right? This is the bushels of apples per tree. Okay, so her harvest would actually be the product of those two things. So this table of values here is not my objective function. It's just helping me think through how I would determine what her harvest is. So number of items times number of whatever we're trying to produce, in this case, apples per item. All right, so 20 times 110, 21 times 105, 22 times 100 would be her harvest. We have variable functions here though, so if I want to write down an objective function using my variable x here, I'm basically going to write an expression for this number of trees. So we start at 20, and then we're going to add some additional trees per acre. So this would be the number of trees per acre that she's going to plant. Starting at 20, but maybe changing. And then her harvest will be that number of trees per acre times the bushels of apples per tree that is produced from these trees. So here we're starting at 110 if we just plant the basic 20 trees per acre, but this is going down by 5 for each additional tree planted. So I can think about this like a linear function that starts at 110 and goes down by 5. So the rate of change here is 5 per tree. So if she produces one more, or plants one more tree, it goes down by 5. 2 more trees, it goes down by 5 times 2. So this is representing the trees, the bushels of apples per tree. All right, so this is the function that I want to maximize her harvest. So I think the hardest part of this kind of problem is getting this function written down correctly. And again, my strategy for doing that is letting my variable represent the number of additional items that it's telling us about, and then thinking about that you probably have one quantity getting bigger and one quantity getting smaller. A table can help you think about how to write those two pieces of this function, and then we're looking at the yield, which would be the product of those two things. All right, so that is my objective function. If you choose to set up the problem this way, your objective function will just be a function of one variable. If you have more than one variable on the right-hand side here, then you need to do some additional work and convert the function to be just in terms of one variable. So using this strategy will help you avoid that step of having to convert a function of more than one variable to just a function of one variable. So I don't need to write down anything about constraints here. If I started with more than one variable here, I might do that and then substitute in so that I have a function of one variable. The other thing that we do in these problems is think about the domain here. And so think about the feasible domain, reasonable values for x. So x is number of additional trees, so that's going to have to be whole numbers. If I get a fraction answer, I'm going to have to round that, so whole numbers here, additional trees per acre. But then thinking about whether x would necessarily have to be positive or negative, I could plant additional trees per acre, but maybe also I could plant less trees per acre and that yield would go up. It doesn't exactly tell us here. So it's hard to know just from the context of the problem whether I could use negative values for x, which would maybe mean we plant less trees per acre. They didn't exactly give us enough information. It just talks about additional trees. Doesn't really say about what about if there are less trees. So maybe x greater than 0, greater than or equal to 0. It doesn't exactly tell us that, but let's go ahead and work with this objective function, and then we'll come back and think about whether we need to restrict our x values. All right, so at this point, it's kind of all setting up to actually do the calculus part of the problem. The calculus part of the problem is finding the critical values and then classifying those as locations of maximum, minimum, or neither. All right, so critical values. That's where I'm going to take the derivative of my objective function and set that derivative equal to 0 and think about where the derivative does not exist. All right, so you might notice here that my objective function is a product. So I can find that derivative using product rule if I want, or at this point, maybe I go back to my objective function and simplify that so that I have a slightly simpler way to find my derivative here. So I'm going to FOIL this all out and combine some like terms so that my objective function is simpler, so that when I take that derivative, it's a little bit easier. All right, so 20 times 110 will be 22,000. And then here I'll have 20 times minus 5x would be minus 100x. And then I'll have a plus 110x. So minus 100x plus 110x will be plus 10x, combining those like terms. You can write that out as separate steps if you want. And then minus 5x squared. So either of these two forms are okay for your objective function, but when you want to take the derivative, maybe you want to use the version that's going to make the derivative a little bit simpler. All right, so I'm going to take the derivative, h prime, and so I'll get 10 minus 10x. And I want to think about where that derivative does not exist. So I'm looking at this function and determining, are there any values of x that make this derivative function undefined? There are not, so I don't have any of those for this one. And then I need to think about where the derivative is equal to 0. So that's when we're going to set our derivative equal to 0 and solve for x. Okay, so I'll add 10x to both sides and then divide through by 10. So I'll get x equals 1. All right, so that's our critical value. That's the location of a possible extreme value. So we need to do some kind of test to determine whether this value actually maximizes, minimizes, or perhaps neither for our function. So there are several different methods that we have used to test. The one I've used in the last couple of videos is using that second derivative. So I'm going to go ahead and use that again here. So I'm going to find the second derivative, h double prime, will be negative 10. And I know that if a second derivative is negative, that the function is concave down. And so our critical value that we have would be the location of a max. So if the function's concave down, the critical value on that region would be the location of a maximum, which is what we wanted to maximize the harvest. All right. So at this point, I've done all the calculus work. I need to just make sure that I answer the question. All right. So I want to determine how many trees she should plant. So our x value was 1, and so that's 1 additional tree per acre. Remember that labeling here at the beginning can really help you when it's time to answer your question, so you're clear about what this number represents. 1 additional tree per acre. Or another way to answer that might be to think about how many total trees per acre she would then plant. So 20 plus 1, 21 total trees per acre. When you're doing online homework, often they'll have a box for you to type in a number and some words written after the box. So just pay attention to what the words say. If they're asking to give the answer for how many additional trees, then you would put 1. If they're asking for how many total trees per acre, then you would take your 1 and add it to however many trees that we start with that we know there. Okay, we'll look at some more videos for some more optimization problems.